What is a friction? When one body slides over another body due to the relative motion, there is a friction which comes into play which is parallel to the surface of contact, this surface of contact. A friction which comes, a force which comes into play, which is known as frictional force. So let's take a, let's take a block. Supposing you're applying a force in this direction, then the frictional force will be in this direction. Okay, so if you're applying a force in this direction, the frictional force will be in this direction. Okay, so then, so let's take a block on the table. You know that an mg is acting downward. There's a normal reaction which is acting upward. There's an applied force in this direction. There's a frictional force in this direction. A small f represents frictional force, and the resultant which can be drawn like this, which theta being this angle, and tan theta itself is frictional force by normal reaction, opposite by adjacent, where this is f, an opposite can also be frictional force by adjacent is normal reaction, f by r, where this tan theta can also be called as mu, which is f by r, where mu is known as the coefficient of friction, which is a constant for a given material. For a wood, it will have different coefficient of friction. For a metal, it will have. It also depends on whether you're sliding it on a table or sliding it on a road. So then it depends on the surface of contact. So then the tan theta is equal to f by r, mu is equal to f by r. Therefore, frictional force is mu into normal reaction. It's a very, very important formula. You'll see me using that in lots of places. Here, normal reaction R is equal to mg, and yeah, okay. So then you must have done this experiment in the lab where you take a block and you connect it to a spring balance, and you keep adding weights here. Keep adding weights here, and you see the pointer will read certain values, certain readings here. Okay, and your applied force in this direction. You're pulling it in this direction. So initially, the body will not move. Why the body does not move? Because the frictional force keeps on increasing as the applied force is increasing. See, supposing you're sitting in one place and I'm trying to put an applied force on you, you will not immediately move. I have to slowly increase my force, because as I increase the applied force, the frictional force also is increasing, reaches a maximum, and then suddenly this is the point at which frictional force, the body is just about to move. It's not, and then it reduces, friction force decreases and becomes a constant. This diagram, this graph is very, very important. It's a graph between frictional force and applied force. This region, which is linear region, is known as static friction. Static friction, because the body does not move initially. As applied force is increasing, the frictional force also increasing linearly. Suddenly, the body, it reaches the, this is known as static friction fx. This is known as fs maximum, the maximum static friction, or it's also known as limiting friction. This distance is also known as limiting friction. And after that, the friction reduces and the body starts moving with a constant velocity, and this is known as kinetic friction. Similarly, you have a coefficient of static friction us. When it comes to static friction is directly proportional to normal reaction. Fs is equal to mu s into normal reaction. Similarly, kinetic friction, Fk is equal to mu k, Fs, which is the limiting friction, is equal to mu s maximum, which is the coefficient of limiting friction to normal reaction. And the kinetic friction Fk is mu kinetic, coefficient of kinetic friction to normal reaction. So the coefficient of friction can be classified as coefficient of static friction, coefficient of limiting friction, coefficient of kinetic friction. So three different, and this graph is very, very important. Friction does, depending on what stage of motion the body is. When the body is not even moving, it's static friction. The body is just about to move, it's limiting friction. When the body is already started to move, it's kinetic friction. So this is a very important graph that they will ask you. And after that, the topic is about why is a rolling friction is always lesser than sliding friction. By the simple fact that sliding, the body slides over another body, shows that there is relative motion at every instant. So when there is relative motion and the surface of area in contact is so much, the area in contact is so much, because in the rolling friction, the wheel rolls, it continuously detaches itself from the surface of contact. So area of contact is minimal, and also there is no relative motion. There is no relative motion because the continuously it's detaching itself. This is what makes the rolling friction. A rolling friction is much lesser than the sliding friction. So now let's talk about a rolling friction. Say take a wheel, it's got a radius r, and you know that the rolling friction will be directly proportional to, always the friction is always proportional to normal reaction, and inversely proportional to radius because it's going to roll, one more component comes into play. Thus the rolling friction is equal to mu rolling, which is coefficient of rolling friction into r by r. When you remove the proportionality, it will become equal to, and a mu r will come into play. So this is the rolling friction, and the fact that there is an r down shows that the frictional force will obviously, rolling friction will be less, mathematically also you know that. Okay, so next is, there are many numericals in Aurora which I have done. Please make sure you are doing all those inclined plane sums, which are all very very important. I've done many. So in the class, I hope you all remember. I can't do a complete video though now. So next is whether pulling is easier than pushing. It's a very important question which comes in every paper. This is a road roller. I'm going to pull it. It has got a handle here, and I'm going to apply a force here and pull it. I know then in that case the force gets divided into two components. This is theta, so this is F cos theta, and there will be an F sin theta component. You also know mg is going to act down, and normal reaction is going to act up above mg. And if it's going to be rolling on the floor like this, the frictional force is going to be in this direction, because you're rolling rightward, the friction will be leftward. So let's resolve the vectors. Can you see r plus f sin theta, the up vector is equal to down vector mg, r plus f sin theta, r plus f sin theta. The r itself therefore is mg minus f sin theta. And you know frictional force is mu into normal reaction, and substitute normal reaction from here is mg minus f sin theta. This is coefficient of kinetic friction because here the road roller is moving. So you have to put mu k here. The fact that the frictional force is lesser, the normal reaction is lesser, makes the frictional force also lesser. When the frictional force is lesser, it's easier to pull. So this is pulling. What happens to pushing? Let's see what happens to pushing. When you're pushing the road roller in this direction, yeah, this is your handle and this is your handle, and you're pushing it like this, then the force is going to be in this direction. And there's this theta, and there's an F cos theta, and there's an F sin theta which is acting downward. And mg is also acting downward, a normal reaction is acting upward. And you're going to push it to the right, so the frictional force is towards the left. And now let's resolve the vectors. R is equal to up vector is equal to down vector mg sin theta plus f sin theta. The fact that the normal reaction is increasing, you know frictional force is equal to mu into normal reaction. So mu into normal reaction is mg plus f sin theta, shows that the frictional force is greater when compared to pulling. Pulling was the negative sign, pushing has the positive sign. Here it's getting added. The frictional force is greater, and that concludes that pulling is easier than pushing. So next is an expression for what is the next thing? I'll have to talk about a circular road, just outside Avin, near Theosophical Society. You have this curved road, right? In such a curved road, you have to come with a certain speed only. If you exceed a certain speed, you will meet with an accident. So then, it's a flat road though, but it's curved. Okay, you have a car which is coming here. The wheels of the car is here. The car. And you know that the frictional force, this is the center of the circular path, and the frictional force will be directly towards the center. There will be F1 and there will be F2 due to two wheels. And F itself is F1 plus F2. There will be an mg of the car which is directly pointing downward, and the normal reactions will be directly pointing upward. And so what can I say? The total frictional force is F1 plus F2, which is mu into normal reaction R1, which is, this is R1 because the wheel is here, one wheel which is pressing, and another wheel is R2. There will be and R is equal to R1 plus R2 is the total resultant upward reaction. mu into R1 plus mu into R2, thus mu into R1 plus R2. R1 plus R2 itself is mg according to up vector is equal to down vector. Therefore, mu into mg is frictional force. The thing is, the frictional force is what is going to provide you with the centripetal force here. The frictional force is this, which is what is going to provide you with the centripetal force, mv square by r. That's a key point. If you forget that, you can't write it. M and m get cancelled. V square is equal to mu rg. V is equal to root of mu rg. So this is the maximum velocity with which you can take a turn. It depends on the radius and the gravity and the coefficient of friction, beyond which you cannot exceed. Okay, so this is a very important derivation for a circular motion of a car on a level road. This is about a level road, but a circular motion. Exact example is Avin, the road near Avin. So next is, what is a bank road? Banking of a road is slightly elevating the road. You know, you've seen in hill stations, the road will be slightly raised. Otherwise, we'll fall into the valley if they don't do that. So then, in the raised road, it's a raised road. You have a car, whose mg is directly downward, but the normal reaction is right above its head, which is crossed. This normal reaction. Okay, so then you have this to be theta. Therefore, this is r cos theta, and this will be r sin theta. R cos theta and r sin theta. So we resolve the normal reaction. Let's talk about the frictional force here. The frictional force is going to be in this direction, and therefore that can be broken into two components. This is theta, so then this will be f cos theta, and this will be f sin theta. So now you don't have to break down the mg, just forget about it, okay? Just remember only till here. So then we're going to resolve the vectors. Can you see that you have this is left vector, down vector, okay. What are the up vectors? Upward vector is r cos theta, which is equal to downward vector, which is simply mg. Okay. Then let's talk about left vector, and r sin theta plus an f cos theta, which is leftward, left arrow, r sin theta plus f cos theta as a left vector, which should provide you with a centripetal force, mv square by r. Okay, and r cos theta is equal to mg. And r cos theta is equal to mg, and r sin theta plus f cos theta is equal to mv square by r. Yeah. So there's some mistake somewhere here. There is r sin theta plus f cos theta is equal to mv square by r. This is correct. What about the other equation? An mg plus, I forgot this downward vector. Okay, so then let's continue. The up vector is r cos theta. R cos theta is up vector, which is equal to mg plus f sin theta. Oh yeah. So then therefore you can move it to that side. Move this to that side. You get r cos theta minus f sin theta is equal to mg. Mark this as 1. Mark this as 2. Divide 1 by 2. You get r sin theta minus f cos theta by an r cos theta minus f sin theta is equal to mv square by r by mg, where m and m get cancelled. So an r sin theta minus f cos theta by an r cos theta minus f sin theta is equal to v square by rg. You have to, you know, frictional force is equal to mu into normal reaction. So mu therefore is f by r. You have to divide it by an r cos theta. Divide throughout by r cos theta, so that the first term will become tan theta minus f by r by 1 minus f by r tan theta. Okay, this is r sin theta plus f cos theta, because this is got a plus symbol. Okay. So tan theta plus f by r is equal to 1 minus f by r tan theta is equal to v square by rg. Therefore, v square in itself is rg into FIR itself is mu, so mu plus tan theta by 1 minus mu tan theta, because you know FIR is mu. So V therefore is root of Rg into mu plus tan theta by 1 minus mu tan theta. That is about the velocity with which a body can go in a raised road, in a bank road, in other words. Okay, supposing in this, there's a case study where if supposing mu is equal to 0, there's no friction on the road, then mu becomes 0, this V can be root of, this mu goes away, this mu goes away, Rg tan theta, you just that you'll have an Rg tan theta. So this is a case study where V square is equal to Rg into tan theta. So tan theta is V square by Rg. So then therefore theta is tan inverse of V square by Rg. Tan inverse of V square by Rg. So this is just a case study, but this formula is very, very important. Next, bending of a cyclist. So bending of a cyclist. Supposing you have, you know that a cycle has got a greater wheel, the R is more, and you know rolling friction, when R becomes more, the friction becomes less, you know rolling friction becomes less because they are inversely proportional. I've taught you that about rolling friction. So therefore there's negligible friction. When there's negligible friction, there has to be friction, right? Otherwise the person tends to fall. So how, in order that, because there's no friction, what the cyclist does is he bends his body like this. He bends his body when he's taking a turn. You must have noticed it. He will bend his body so that he gets two components, this theta. So this will be r cos theta and this will be r sin theta, where the r sin theta component will provide the centripetal force, will provide the mv square by r. This component r sin theta will provide the, so this is the cyclist. So when he bends his body, two components comes into normal reaction, and so then r sin theta gives mv square by r, and r cos theta will be equal to mg. Upward will be equal to downward, so r cos theta will be equal to mg. So you can divide one by the other, you get tan theta is equal to v square by rg. So again you get theta is equal to tan inverse of v square by rg. This is for the bending of the cyclist. Okay, so then therefore the radius of the curved path is small, or the curved turn is sharp, theta, the angle theta through which the cyclist bends would be greater. The angle through which he bends will be greater. Obviously if r is small and also the speed of the cyclist is larger. Just mathematical expression. This is very, very important, bending of the cyclist. Okay, so that's this is all the rotational motion part. And the last but not the least is the stone which is tied to a rope. It's going to rotate about like this. Now at the bottommost point, you know the velocity is initial velocity u. This is radius r. Supposing this is at a height h, then this will also be at a height h, and therefore this height h, and therefore this part will be r minus h from here to here, will be r minus h. Okay, so then that's r minus h. You can construct this into right triangle. This is theta. You know that the bobble is at an mg downward. This will also be theta, so there will be an mg cos theta, and there will be an mg sin theta. There will be a tension in the string. And what is, you know, this tension, this is also radius capital R of the rope. You can take this triangle and write cos theta is equal to adjacent, which is r minus h by capital R, and you can keep this equation as it is. Then this is, the ball reaches this point at any instant of time. Okay, at the lowermost point, at this point, you know the total kinetic energy, total energy is kinetic energy plus potential energy. The kinetic energy at the lowermost point will be maximum, which is half mu square, which is the initial velocity, plus potential energy is 0, plus at this point what happens, when at this instant of time what happens is the total energy, which is kinetic energy plus potential energy, will be half mv square, considering the velocity at that instant is v, plus potential energy is mgh. So equating both of this by conservation of energy, half throughout can get cancelled, you can put a 2 here, m throughout can get cancelled, thus you get a v square is equal to u square minus 2gh, or b is equal to root of u square minus 2gh, which is the velocity at any instant, velocity of the stone or the ball at any instant. Okay, the motion on a vertical circle. This is about vertical circle. Revision about vertical circle. So after writing this, you have to go back to the diagram. Can you see an mg cos theta is outward and a tension is inward, and a T minus mg cos theta should provide the centrifugal force. This T minus mg cos theta should provide the centrifugal force. So let's write that statement. T minus mg cos theta should provide the centrifugal force, which is mv square by r. Very, very important statement in here, because you know what is cos theta. You found this with equation 1. You found velocity, which is equation 2. So you can substitute for v as well as for cos theta. T is equal to mv square by r plus mg into cos theta, and a v square itself is u square minus 2gh by r plus mg into cos theta is r minus h by r from the first equation, r minus h by r. R is the radius, you can keep it as capital R. So you can take m by r common. You have u square minus 2gh plus m by r has been taken common, plus gr minus gh. So this and this will add up to minus 3gh. So m by r into u square plus gr minus 3gh is a very important formula for tension in the string at any instant. Now tension at the lowermost point. At lowermost point, you know, height is equal to 0, h is equal to 0, this h. So tension at the lowermost point will be m by r into u square plus gr. Tension at the highermost point, where h is equal to 2r, at the highermost point it will be r plus r into the total height in the surface, so then 2r. So in that case, if you substitute h as 2r, you get an m by r into u square plus gr minus 2r, 6gr it will become. So then the tension at the highermost point therefore becomes this, and the tension at the higher, where the tension is maximum? At the lowermost point, the tension will be maximum this time, because the stone will pull it down. Tension lower minus tension higher is the tension difference between the lower and the higher point. Where m by r is common, you got this as equation. This is equation 3. This is equation 3. This is equation 4. This is equation 5. You're going to subtract 5 minus 4. So then u square gets cancelled, gr gets cancelled. So you'll have just a 6 gr, and r get cancelled, so 6 mg. This is the value for tension between the lower and highermost point. Okay, then next is about if this has to looping of loop should occur. Looping of loop means it has to go around. You have, what is the velocity u that I have to give so that it will go around like this, for which the tension at the highermost point should be greater than 0. Tension at the highermost point formula is here. This is the tension at the highermost point, which has to be greater than 0. M by r into u square minus 5gr has to be greater than or equal to 0. U square has to be greater than or equal to 5gr. So u has to be greater than or equal to 5gr. That is the minimum velocity that you have to give so that it will whirl around. It will looping of the loop will occur. It will not slack and fall off. Okay. So till here it's very, very important. Then let's look at the velocity at the highermost point. What is the velocity at this instant? You know, the velocity at this instant is velocity v is equal to root of u square minus 2gh, where h itself is, as you know, 2r. So u square minus 2r, when you substitute 2r, it will become 4gr. And you know, u square itself has to be 5gr for looping of loop to occur. So root of 5gr minus 4gr. So what should be the velocity at the topmost point for the looping of the loop to occur is root of gr. So therefore, you know, at the lowermost point, you have to have a velocity root of 5gr minimum. Highermost point, you should have the velocity root of gr for looping of the loop to occur. What about if it's going to oscillate? We've done a sum like this. The bob is here. It's going to come here. Okay, it's going to come till there, and it's going to come down. What is that meaning? Then the entire kinetic energy is converted into potential energy, because the maximum height, okay, that here the height is itself r, and entire kinetic energy, which is half mu square, will get converted into mg r, h is r. Therefore, you can say, you can find whatever is the velocity, m and m get cancelled. Therefore, u square is equal to 2gr. So that's the velocity with which it's got to be pushed in order to that it reaches only this height. Okay, because that's only height is just r there. So I hope you understood. This is just the derivation part of the lesson. There are so many numericals in Aurora which you should have tried obviously. I have done many sums in class. I'm not able to give you a recording, entire recording in detail now. Please open Aurora and do the sums after this, okay?